Welcome back, everyone. Today we're dissecting a ghost from 1997. The Piper's Row car park collapse in Wolverhampton. Imagine a massive concrete structure designed with the best technology of its time, suddenly giving way without a single warning. No earthquakes, no overloads, just a quiet night at 3:20 a.m. While the city slept, that turned into a structural nightmare. The top deck didn't just crack, it vanished into the floor below. This wasn't a random accident. It was a fundamental failure of what we call punching shear, triggered by a hidden enemy that had been eating the building from the inside for years. Let's look at why this unbreakable slab failed. To understand the collapse, we first need to understand the strength. This car park used post-tensioning to create active compression, essentially squeezing the concrete to make it incredibly stiff. We won't go into all the details here. If you want to see exactly how these high-strength steel cables turn a limp piece of cardboard into a rigid bridge, I highly encourage you to check out our previous videos on post-tensioning. For today, just remember that internal squeeze is the primary force holding the slab together. But every hero has a weakness. For Piper's Row, it was water ingress. Over years, rainwater mixed with road salts leaked through tiny cracks and joints. This salty cocktail reached the anchorages of the post-tensioning tendons. Think of it like a slow poison. You can't see it because the steel is buried deep inside the concrete. The salt triggers corrosion, which is like 1,000 tiny saws cutting through those vital steel strings. As those of you who follow our channel know, these specific tendons were unbonded, meaning no protective grout. So once a single wire snapped, the loss of tension wasn't local, it traveled along the entire length. When those tendons corroded and snapped, the slab lost that vital squeeze. If you suddenly remove that active compression, the structure doesn't just sag, it fails instantly. In the Piper's Row slab, the post-tensioning wasn't just helping with the load, it was providing the shear strength needed to keep the slab attached to the columns. Without that horizontal squeeze, the concrete was forced to rely on its own internal tensile strength, which, as we know, is incredibly weak. The slab became a heavy weight, just waiting for gravity to take over. Now comes the moment of failure, punching shear. Think of a pencil pushing through a thin piece of paper. The paper doesn't snap in half, the pencil just punches a hole right through it. In engineering, the column acts like that pencil, and the slab is the paper. Under normal conditions, the post-tensioning creates a compression zone around the column that resists this. But with the tendons gone, the stress concentrated at the column head exceeded the concrete's capacity. A diagonal crack formed, a truncated cone of failure, and the slab literally slid down the column. It's a sudden, brittle failure, meaning there's no bending or warning. It just happens. The scariest part? Inspectors had looked at this building, but they used visual human inspection. To the naked eye, the surface looked fine. The corrosion was hidden inside the ducts, like a silent disease. Our static design codes at the time didn't fully account for how quickly unbonded tendons could deteriorate in a parking environment with salt and water. Ironically, the UK had recently recognized this exact danger and started restricting unbonded tendons in new structures. But for older buildings, we were still relying on their outward look, and this building was lying to us. It's a reminder that what we can't see is often more dangerous than what we can. So, how do we stop the next Piper's Row? The answer lies in the transition to the future: structural health monitoring. Imagine if the building had a nervous system. Instead of waiting for a human to walk by once a year, we install sensors, fiber optics, acoustic sensors, and strain gauges that listen to the tendons. If a single wire snaps, the building screams a digital alert to an engineer's phone. We move from reactive maintenance to proactive intelligence. We stop guessing and start knowing. The Piper's Row collapse changed how we view post-tension buildings worldwide. It taught us that durability is just as important as strength. We can build slabs that span incredible distances, but if we don't protect the muscles inside, the skeleton will eventually fail. As engineers, our job isn't just to design for the day the building opens, but for the 1,000 rainy days that follow. We must respect the chemistry of the environment as much as the physics of the load. But having a nervous system is only half the battle. A building also needs a brain. What happens when we connect these structural health monitoring sensors to artificial intelligence? In our next video, we'll dive into how machine learning models are analyzing massive streams of structural data to predict failures before they even start. It's no longer just about buildings that talk. It's about predictive algorithms that listen, learn, and save lives. Stay curious, stay rigorous, and I'll see you in the next lecture at Strong Foundation Engineering. If you found this breakdown helpful, hit the like button, share the video, and subscribe to join our engineering community.